So welcome back again. We're going to finish up lesson 11 here by sort of taking a combination of all the materials systems that we've been talking about, metals, ceramics, and polymers, and bringing them into the concept of composites. It's typically an area that sometimes doesn't get the attention it quite deserves when we start thinking about the wide range of uses for composite materials in structural areas and in other areas that we typically will run into different types of materials. Now, composites, as we know from Boeing's use of composites in the aerospace industry, are definitely an area of interest for lightweighting and higher performance. But it's good to sort of take a look at what some of the basics of composites are, and that's what we're going to sort of get into. And so the quote for today comes from Thomas Edison. Couldn't really get something from Edison, as you can tell from the quote as you read it. He was probably not the most pleasant supervisor or boss to have. He did not really care if you tried hard. He expected production and accomplishment. He was to the point where he did not keep clocks in his labs in New Jersey. So just think of that. Some of you might be fortunate or unfortunate enough in your working lives to have a supervisor or manager or boss like Thomas Edison. So let's get into composites a little bit. What we're going to do is really look at different classes of composites. We're going to take a really broad overview of what composites are. And what we're going to see is that composites are basically a combination of two different types of materials, where we have a matrix material and some type of reinforcing material that gives it strength. So typically what you'll see is the matrix give one property, the reinforcing material gives another property, and that's what gives it its overall composite structure and capabilities. So of these different composites, what we can look at is this reinforcement material can be either a particulate or a fiber. And the matrix material can be composed of either a polymer, ceramic, or metal. So when you start looking at it, there are two broad classifications of reinforcement, which are either particulates or fibers, and then three broad classes of matrix materials, whether they're metals, ceramics, or polymers. And so, as always, I recommend read the Callister textbook on these areas. I'll give a little more detail than what I'll go over in the lecture, as well as make sure that you do the two practice problems, as well as go through the other problems that are given as recommended problems. You will see things like these on the upcoming exam. So just as with ceramics, just as with polymers, composites have certain terminology to keep in mind, and we sort of hit upon each. The one that I would concentrate more on is continuous versus discontinuous fibers, because if you go back to here, you'll see the influence of fiber length. So being able to understand what that actually means is important in the design and the ultimate properties of a composite structure that may be fabricated. So what makes a composite work? I think the sort of simplest high-level view of composites is composites are really trying to get the best of both worlds, where you have a material that may be rather ductile and you want to increase its strength, so you add a material that's rather strong but has minimal ductility, because usually you can't get both. So composites are really a way to sort of split that difference in either high strength or low ductility, or high ductility, low strength. So it splits the difference by combining material and sort of this principle of combined action. Material properties can be enhanced one way or another by getting these materials that have these significantly different properties and combining them. They typically are multi-phase materials, so that the reinforcement particles are much different than the matrix material. That's why you can have a metal matrix composite, or a polymer matrix composite, or a ceramic matrix composite, depending on your application. So they have this matrix and this dispersed phase, and so a lot of cases, the dispersed phase, its size, shapes, distribution, its orientation, is going to give you a lot of the properties of what we have out of the composites. So if we look at the general classification, it sort of comes back to what that reinforcing medium is. It can be particle reinforced, and when we look at that is you can have large particle or dispersion strengthened. So it's like a large particle and a small particle. Dispersion strengthened is another way of looking at small particles. In the fiber reinforcement, you can have continuous or discontinuous fiber, so that depends on the fiber length. And in the discontinuous, if they can be aligned or randomly oriented, it gives you different properties. You can have very good properties in one orientation with a continuous aligned fiber, or with a discontinuous randomly oriented fiber, you can have a little lower properties in all directions, but more equivalent. And then when we start getting into structural composites, these can be laminates. Plywood is a great example of a laminate type structural composite, or what we will see as sandwich panels. And so what we'll see is that there's a design component as well as a materials component to structural composites. So as we work our way through, let's get into particle reinforced composites. So there's a distinction between that. As we look at the classifications, we can have a large particle or a dispersion strengthened composite. So it depends on what is going on. So in large particle composites, there are a couple things to keep in mind. Is that particle matrix interactions are at a little higher scale. They're what we consider a mesoscale rather than an atomic scale. The particulate phase is typically harder and has a higher stiffness than the matrix material. And what the reinforcing particles tend to do is they keep that matrix. The matrix tends to be more ductile than the particulates that are added, and they tend to restrain the movement of the matrix. So they're halting dislocation motion if you're thinking of a metal-based composites. But the matrix is also able to, since it's more ductile, is transfer some of that stress to the particles, which can bear that load. Now, dispersion strengthens tend to operate at a little more of an atomic level. So the particles are much smaller. They're in the nano size range typically. The particle matrix interactions, the strengthening occurs a little more at that atomic level. So you have much smaller defect distributions. And it's very similar to what we saw with precipitation hardening with aluminum-based alloys, except we're adding on purpose what are typically oxide particles. What you typically will see is oxide dispersion strengthened alloys are one of these that we would see. And so the matrix will bear most of the load, and these small particles will hinder the motion of these dislocations. Very similar to what we see with precipitation hardening. So in dispersion strengthened composites, you can think of them really as an artificial precipitation hardening mechanism. So large particle composites, we see the cemented carbides. What we would see in this is drill bits and different types of applications in this. So we have a tungsten carbide particles in a cobalt matrix. This is something that has a very high hardness, very high wear resistance, something you would need for a drill bit to go through rocks. Carbon fiber, this is basically tire rubber, synthetic tire rubber. And that is, for the most part, a large particle reinforced composite. It's just a polymer matrix, while this is a metal matrix composite. The cemented carbides are metal matrix composites. So with that, what we have is with these different large particle composites, depending on the volume fraction of the constituent phases, how much of that particle do we want to add? Or another way to think about it is how much do we load that matrix material up with these large particle composites. And so the more you get of these particulate materials, the closer you're going to get to what the actual reinforcing material properties are going to be. So there is sort of what we consider a rule of mixtures, where there's an upper bound and a lower bound. In this case, what we're most concerned about is the modulus of elasticity, of the stiffness of this type of material. And so how much we add of that matrix material and the particulate reinforcement is going to give us the higher end of it, and then we'll have a lower bound to it, which will take a little more complex feature to it as we start adding in different particulates. So this allows us to give us sort of an upper and lower bound of what type of stiffness. So we can start tailoring properties based on how much of the particulate we might want to add to the composite material. Now, dispersion strengthened composites, you're typically going to be this uniform distribution. The oxide material, as we said, hinders dislocation motion. And so what you tend to see is you have this dispersion. It's about 3 volume% of small oxide particles can have very significant impacts. In this case, we're thinking of nickel-based alloys on strength. So that upper and lower bound is going to be different depending on the size. So dispersion strengthening takes on a little different perspective to it. And we want to keep those particles small, just like we do in precipitation hardening, to allow us to be able to stop the dislocations from moving through the material. Now, these are commonly used. Oxide dispersion strength, I should say, is they're a class of alloy. They have been used. They're not used as much as you might really think, because they're very difficult to process. They require powder-based processes to process in order to obtain this distribution of these particles, and then they need to be ball milled and a lot of other things to build to sort of integrate these fine oxide particles into the matrix material. So they're not widely used. Most of the companies that started out in this business have either gotten out of it or gone bankrupt. You see a lot more large particle composites, particularly for these types of cutting, cemented carbide type applications. But the more common of the composite materials you're going to run into are what we look at as fiber reinforced composites. And what these are high strength and stiffness per weight. So we can call that specific strength or specific modulus. What we're trying to do in fiber reinforced composites is, for the most part, lightweight something. If you go to Lowe's or Home Depot, you don't really see a lot of metal ladders anymore. And the ladders are lightweight because they're made from fiber reinforced type composites. And so it's going to depend on the properties of the fiber and how that load is transmitted from the matrix to that fiber. And so in order for that to happen, there's a couple things to think about. The first one is how long the fiber needs to be to give you effective strengthening. So if fiber's too short or too long, it's going to give you something. So you want a critical fiber length. And this is going to lead us into that continuous versus discontinuous fibers. But you need to have this ability to have a fiber of a certain size. Now, one thing that goes into that, that's sort of that second thing to really think about, is how well the matrix and that fiber are bonded together. Because you can also, if they have a poor bond between the matrix and the fiber, what can really happen is that the fiber will literally pull out of the matrix without giving you any strengthening. And that's something you do want to avoid in fiber reinforced composites.